So, good afternoon and welcome back to the lecture series session of CNC. In the last couple of weeks, we had discussed about the different types of interpolation, that is the point-to-point interpolation and the straight line interpolation. And third is the remaining part. Today we will discuss about the circular interpolation, which is also extremely important in case of CNC system. So, content-wise, what is circular interpolation, how it is been implemented, those points we will discuss first, followed by derivation of the summation formula similar to the straight line interpolation. Same type of summation formula will be derived, and finally how a curve can be approximated by straight line, that is what exactly is carried out in CNC system along with some tolerance analysis. So with this, let us first move to the typical criteria or aspects of circular interpolation. So circular interpolation in CNC is used to generate any circular profile such as fillet, spherical radius, etc., which are frequently encountered in mechanical components. To generate any circular profile, the programmer will have to specify the coordinates of the start point, the end point, and the components of the radius vectors along two orthogonal axes in the plane where the profile is generated. This particular aspect we will discuss in detail when we will undertake the CNC programming, how to implement the G codes for the circular interpolation. So just for the time being, what is essential to implement a circular interpolation, we ought to specify the starting point coordinate, end point coordinate, and the two orthogonal components of the radius vector in the particular plane where that particular circular interpolation or the particular profile is being generated. Just for the time being, once again, this circular interpolation is implemented by typical G codes which are identified as G02 and G03 respectively for clockwise and counterclockwise motion. Because depending on the scenario, depending on the nature of tool movement, we can have clockwise movement or we can have anti-clockwise movement. And to distinguish clockwise from the anti-clockwise, two separate G codes are used. G02 is for clockwise and G03 for counterclockwise. If you can recall, similar G codes were used in case of PTP and straight line. For PTP it is G00, for straight line interpolation it is G01, and it is G02 and G03 for clockwise and counterclockwise circular interpolation respectively. Now this is the most important aspect to consider, to memorize. Since the machine axis do not revolve around the center, true arc generation is not possible. It is misnomer to consider that a perfect circular path would be generated in case of a CNC. That is never possible. Because once again, if you can recall the discussion of straight line interpolation, along the typical direction of the straight line, it is never possible to exactly generate the desired path. So it would be essentially the resultant motion of the two mutually orthogonal axes, that is x and y or x and z. So it is basically approximation. So obviously there will be some error. The same logic equally also holds true in case of I should say the same limitations also holds true in case of circular interpolation. So exact circular path can never be generated. So this circular path is basically approximated by a small straight line segments. So in essence, circular interpolation in CNC is a move consisting of series of small straight line chord segments in a two-dimensional plane to simulate a circular arc. So entire circular arc which we require to be generated, that is broken down into small rectangular straight line circular chords along which the tool path will be generated. So essentially what we are doing, we replace or we approximate the circular path as a closely broken down small chord segments so that we can generate an approximate circular path instead. So these chord segments are very small and therefore together closely resembles an arc. So the error is not substantially high and it is acceptable for mechanical applications. Now for this purpose, eventually similar to the straight line system, two summation formulas are used. One is x equal to x nu, which is approximately can be written as x1 minus summation of y nu minus 1 minus yc divided by n, and the summation is taken over where nu varies from 1 to mu at any particular instance. Afterwards, I will be moving toward its derivation. And similarly, for y-axis, the similar expression is there. Now, let us have a look how this interpolation or the summation formula can be developed. In this case, the approach is little bit different from that of straight line interpolation. Now, I have taken a circle having a radius r, having the center point C with a coordinate xc and yc. Now, when the tool is moving in space, it is assumed that it must have a definite velocity. So that is why we have considered as if the tool is moving with a constant angular velocity, that is omega. P is an any intermediate point having dynamic coordinate system as x and y. Now this P at any instant makes an angle phi with the x-axis. Now in this case, in earlier case when we had discussed about the straight line interpolation, we had considered from point P1 to point P2, and this entire region P1 to P2 along x and along y, those are decomposed into n number of small segments, so that with using n number of discrete pulses, eventually the cutting tool will be able to move from point P1 to P2 as far as x-axis and y-axis separately are concerned, and eventually the resultant motion would be the net resultant of x and y motion. Now in this case, how it differs? Let us consider t0 is the time required to traverse a unit arc. What is unit arc? Unit arc is basically the angle subtended in the center which corresponds to 1 radian. Okay, so if you convert this 1 radian will be approximately 57.3 degrees or something like that. Since it is moving with a constant velocity omega, so we can write the phi, that is the angular displacement phi, that will be equal to omega into small t. If we consider the time required to move or to generate phi angle at the center is t, then phi will be equal to omega t. But when we consider the same thing for 1 radian angular movement or unit arc generation, then same we can write 1 equal to omega t0 if t0 is the corresponding time for generation of unit arc. So by combining these two equations, if we can eliminate omega, then we can have phi equal to small t by capital T0. Mind that T0 is constant, it is only a particular, assumes a particular value when it is associated with the generation of unit arc, whereas small t is variable. Now from the geometry, it is very simple to calculate the x and y coordinate. I am returning once back to the diagram. So for P, its coordinate is x and y. So x will be how much? If the radius is r, then definitely the coordinate x will be equal to xc plus r cos phi. So that is what exactly is written over here. So x equal to xc plus r cos phi. Now this phi is replaced by small t by capital T0. Here the next step would be to take the derivative. That means if we take dx dt, the objective is that for incremental time movement, what will be the corresponding incremental x movement. So if you take the derivative, dx dt will be equal to minus r into 1 by T0 sin small t by capital T0. So if we take it minus r by t0 as a single unit, and this sine t by t0, once again from the geometry, if we look at this particular expression, y equal to yc plus r sin phi, the way we have considered x equal to xc plus r cos phi. Similarly, for y equal to, we can write yc plus r sin phi, and once again if we replace phi by t by capital T0, you can have sin t by t0 will be equal to y minus yc by r. So a small amount of rearrangement will give you to attain this particular relationship. So what will happen? This r and r will cancel out from numerator as well as from the denominator. So what will be left will be equal to minus 1 by capital T0 into y minus yc. Now for implementation of the interpolation function in digital circuit, this dx is approximated to delta x and dt is approximated to delta t. Once again I am reiterating, similar to the previous one, that we do not have any interest about this dx dt derivative. We have to focus our attention that how this concept will be implemented in a digital electronic circuit. That is most important. That is why this dx dt is approximated as delta x and delta t respectively. So approximately you can be written as delta x equal to minus 1 by t0 y minus yc delta t. Now how it will be executed? Start point P1, end point say P2, that is the two extreme points between the circular arc. So with the issuance of one discrete pulse, the tool will move some incremental distance correspond to delta t time. So to make it amenable, it is written as x equal to x1 plus delta x nu. So nu varies from 1 to mu. That means for any mu number of instantaneous value, if nu assumes incremental values or integer values 1, 2, 3, 4, finally mu, then this additional incremental value we have to add with the previous value to get the current of the recent one. So if you replace this delta x, okay, we can have this particular relationship. Now one step has been omitted over here. Now all of a sudden how n can come? Thing is that if you replace that for one incremental pulse, the corresponding time element is say delta t dash, and since t0 is much longer time duration, this can be considered as a integer multiple of this delta t0. Okay, so if that is so, we can write delta t equal to delta t dash and t0 equal to n delta t dash. So delta t dash will cancel out from the once again from the numerator and the denominator. So what will left in the denominator will have one n value. And since this y is basically a dynamic point, successively you have to consider, that is why this y is replaced as y nu minus 1. So nu varies from 1. So when nu assumes a value of 1, it will be y0 minus yc by n. So that incremental value every time we have to calculate corresponds to every incremental pulse, and that value we have to algebraically add it with the initial value to get the most recent one. So this is how series of intermediate points will be calculated along x as well as along y, because the motion will be simultaneous along xy, or if it is a turning center, in that case it along x and z. So same logic is applied in case of y axis. Okay, so only noticeable parameter or interesting fact is that in this particular expression of x, it is x1 minus this much, and in case of y it is y1 plus this much. This is owing to the fact, if you go back to the previous drawing, you see as the point P is moving from the first quadrant from this point towards the left or in the anti-clockwise direction, with the passage of incremental movement, delta x value or the instantaneous x value, coordinate value, keeps on decreasing and y value keeps on increasing. If you just take any two intermediate points, so someone is here and someone is here, so you will find as it is moving anti-clockwise direction, so instantaneous x value keeps on decreasing, y value increases. So that is why there is a negative sign over here, and in case of y it is positive. So these two equations, number 1 and number 2 together called summation formula, similar to what we had derived in case of straight line interpolation. Okay, so once again I am telling that it is extremely important to remember that there is no such mechanism in NC-CNC system to guide the tool so that it can generate exactly desired circular path. It is approximation by using a multiple number of small straight line segments. In this regard, what is really important to discuss the approximation of an arc in NC-CNC system. Okay. So a curvilinear continuous path is approximated by the aggregation of small straight line chords as shown in the figure. I will come to the figure in the next slide. As the number of line segment increases, the tolerance T decreases and accuracy is improved. As T approaches 0, the number of line segments becomes infinity. To understand this in its true spirit, let us focus our attention, or let us have our discussion with respect to this particular arc segment. Just I have arbitrarily taken an arc which is generated by, or which is shown by this AB having center at this particular point. Now this is our desired path. We would like to generate this circular path, but eventually it is approximated by 3 straight line equal length chord segments. While doing so, there is an error. What is the error? What would be the maximum error? Because every time as the tool is not passing exactly through the desired circular path, rather it is following this yellow color straight line path, so there is an error. Error will be the coordinate values of the point on the actual path and what is in the reference path. And as the tool is moving along this yellow color straight line path, every time you will find this much is the error. Now this error is maximum at the center of that particular chord segment, which is shown by this red color line, and the amount is known as T. That is what exactly is called tolerance. It is quite obvious that instead in this particular drawing I have divided this AB chord your circular arc segment into 3 different or identical straight line chords. Instead of having 3, had it been increased to 8 or 10 or any larger numbers, then this tolerance of this error would have been much lower. And as the number of this line segment increases and approaches towards infinity, so if we assume a very high values of line segment, that is the number into which it is divided, definitely this error part will keep on decreasing, and when n is assumes infinity, it will be literally 0, but that is never possible. So the objective is that we have to focus our attention to the maximum permissible limit of the tolerance. Okay, I will return back to this particular drawing afterwards. So that is what exactly is the interpretation of this second point. As the number of line segments increases, the tolerance T decreases and accuracy is improved. So as T approaches 0, the number of line segment becomes infinity. So to have a realistic approach, it is imperative to limit the value of T to a reasonable level, and accordingly the controller will determine the exact number of line segments into which the entire curve can be divided. So how to develop the relationship for a given value or limiting value of T, what should be the total number of line segments into which the machine control unit will divide the entire circular arc as a part of approximation. This is what exactly is approximation of an arc by straight line segments. So refer to this particular drawing. So I have assumed the radius of curvature of this particular arc is small r. Arc is covered by the represented by the AB line AB segment. D is the distance from the center to this particular point, that is the mid point of the straight line chord segment, and T, that is the red color part, that is the tolerance, which will limit or restrict the number of line segments into which the entire arc will be divided. Now the entire included angle, the angle subtended by the arc AB is at the center is say phi, and since these three line segments are all of equal length, definitely the angle subtended by individual chords will also be identical. Let us consider that particular individual angle subtended at the center by individual chord is theta. So you can easily say, if generically you can say that number of line segment is n, then theta will be equal to phi by n. So for example, if phi is 60 degree and if we assume that there are three line segments, then angle between individual chord segment will be 60 by 3, that is 20 degree. So generically theta equal to phi by n. So that is what exactly is written over here, theta equal to phi by n. Now from the geometry it is also very clear that what will be this d distance. If this is r, so d will be, so this angle is theta, so only this much portion will be theta by 2 any side. So that is why d equal to written as r cos theta by 2. Now how to get the value of t? Once again referring to this figure. So small t will be how much? R minus d. Now d equal to r cos theta by 2. So t equal to r minus r cos theta by 2. Take r common, we will have 1 minus cos theta by 2. And finally you can have cos theta by 2 equal to 1 minus t by r. From we can have theta equal to 2 cos inverse 1 minus t by r. Therefore, you put the value of theta in this particular expression, you will easily get what should be the number of value n into which the entire arc can be divided into line segments. So that will yield phi by 2 cos inverse 1 minus t by r. So for a given circular arc, once phi is known and of course curvature will be given, so knowing the limiting value of t, n can be calculated. But one thing we should remember or bear in mind, that based on the value of phi and r and t, n may not be integer, but n has to be integer. So under that circumstances, one should be careful. The calculated value of n should be rounded to the next higher value, and accordingly new value of phi has to be determined, because there is no such guarantee that by virtue of calculation n will be always integer. Okay, so in that case we have to take the next higher value or rounded value, and accordingly phi has to be determined separately. So that is another source of error. But once again I am telling that the amount or magnitude of error is so small that it won't adversely affect the performance of that particular mechanical components. So finally the new endpoints are computed using the updated values of n and phi. So this is the mathematics behind the circular arc generation. So once again, what is the final concluding part of the circular path generation? It is never possible to generate circular path perfectly, rather it has to be approximated by a number of straight line segments. And what should be the optimum number of line segments into which it will be decomposed? That is governed by or regulated by the tolerance. Under no circumstances that tolerance limit would not be exceeded. So keeping that in mind, the values of your phi, the modified values of phi, depending on the rounded of values of n, the new points, coordinate points can be calculated, and that approximated path can be generated. And since absolutely there is no such circular path can be generated, so it is basically approximation of the straight line. That is why there is as such no numerical problems can be solved considering exact circular interpolation. Okay, so that this completes our entire interpolation part as far as NC CNC machine tool is concerned. In the last two classes, we had discussed about the point to point, which is extremely important for drilling machine. For straight line interpolation, that is equally applicable in turning center and machining center. And another important part aspect which we very frequently encounter while generating spherical radius or fillet radius, this circular interpolation. And the corresponding G codes you have to correctly incorporate in the programming, otherwise system will not be able to implement or distinguish whether you are looking for PTP motion or straight line motion or circular. G00 is the code for PTP, G01 is the code for straight line motion, and G02 and G03 are for circular clockwise and anti-clockwise motion. Okay, so that completes our interpolation part. That is a very extremely important topic, and this is one of the powerful tasks which the data processing unit of the machine control unit is supposed to execute. Okay, thank you very much. Thank you, sir, for your help and support. Thank you.